Okay, so we meet again. So today I'm going to be presenting on neural networks. And I guess here it's always good to mention some good resources. On Monday, when I was introducing machine learning, I mentioned that this is a good book to read, Pattern Recognition and Machine Learning by Bishop. It's a good material and was also one of the sources for the content I'll be presenting today. This is also another nice material by the same author. There's a free version that's available online. You can actually just read it online on the website. It's called Deep Learning Foundations and Concepts, written by the same author in, really the same style as the other book. This book, I think, was published around 3 years ago, so it's really recent and contains a lot of material on frontier concepts in machine learning. Another really nice material I thought I should share with you is this one here. It's called Neural Networks from Scratch with Python. So if you're the kind of a person who just who's curious enough to want to build a neural network from scratch without using libraries like scikit-learn and maybe PyTorch or TensorFlow, this is a nice material because what they do here, the authors they're not researchers, they're just curious people. So it's a nice material to read. Neural networks from scratch with Python. They explain really all the tiny building blocks of neural networks. I think it's a nice material for you to just go through. I think they also have some YouTube tutorials, the authors, so you can check it out. Nice. So now that we have that out of the way, we can get started. So there'll be 2 classes today on neural networks. One is this one which I'm teaching, and then Emerson will be teaching another one after this. So yeah. So what we'll be exploring basically is why neural networks, not neural networks, but why linear models in general fail to, why we don't use nonlinear models for most of the advanced tasks that we do today, right? We'll also look at the biological inspiration behind neural networks and how to design multi-layer perceptrons. Multi-layer perceptrons basically are what we would refer to as vanilla neural networks that have existed for a really long time, and how they work basically and how they learn. So here we remember from our class on linear models and linear regression that a typical linear model will take an input vector x, which is d-dimensional. So basically a single vector that has d elements inside of it. And then it will predict a target value using a linear combination of the input. So this W transpose X is really a linear combination of the elements of X using the weights in the weight vector W, and then add some bias. So this is a linear model, typical linear model. And W is is the weight vector, B is the bias parameter. So you can think of it as even your typical line, straight line, y is equals to mx plus c, it's like linear regression, where m in that case, which is the gradient, is a single element of the W vector, and B is the bias parameter, which would be the intercept for your straight line. One of the reasons why linear models are very attractive is because they have a convex loss surface, right? So when you plot the loss function as a function of the parameters, it's convex in nature. So when it's convex, we know that the global minima is the same as the local minimum, and so The convergence is very fast. It's, you know, the optimization process is very straightforward, okay? But the limitation with linear models is that they form linear decision boundaries, so linear prediction surfaces. So if you have an nonlinear function that exists out there in nature, predicting it becomes, or rather modeling it becomes very challenging, right? And you can often end up with high bias. So sometimes you'll train a linear model to try to fit it on some data, and it fails spectacularly. And it's because the underlying relationship in the data is nonlinear. So you cannot use this model. In that case becomes totally useless, right? We try to extend the idea of linear models to fit nonlinear data using fixed basis functions. And we came up with this function here, where we have some basis function phi j of x, which can be nonlinear. So it's a nonlinear transformation of x. And we say that this function, even though it is nonlinear in the inputs x, it can be viewed as linear in the parameters. So we use this vector notation, and yeah. So the model is linear with respect to x, but it remains linear with respect to the parameters w. So that linearity that exists in the model becomes a problem when you want to generalize this to nonlinear data, or data that doesn't have linear relationships. We looked at some basis functions, polynomial basis function, Gaussian basis function, a sigmoid basis function, which basically squishes the data so that it fits in the range 0 to 1. So these are the common basis functions. This is a polynomial. This is Gaussian basis function. So if you look at these curves, they are just multiple Gaussians together. And this is a sigmoid. In this case is forcing all the values that you put into it into the range 0 to 1. That's a convenient observation. Okay. So these fixed basis functions, they break up at some point, or rather they break down at some point, all right? And we cannot use them with machine learning. And this is primarily because of the issue of the curse of dimensionality. When you have very high dimensional data, you run into serious problems. Not serious problems in the sense that you cannot fit the data, but rather serious problems in the sense that the number of computations that you need to perform becomes ridiculously large, all right? So if the input space X has very high dimensionality D, the number of required basis functions M grows exponentially with D. So an example is that if you have 10 basis, if you have data that requires you to use 10 basis functions along each dimension for a 3D input space, 10 to the 3, so you need 1,000 basis functions in total, all right? And if you are dealing with a 100-dimensional input space, I should tell you, that's a very small space. Sometimes you might be dealing with data that has thousands of dimensions. And so like a 10 by 10 image for an example, if you take a 10 by 10 image and you flatten out the array, that's 10 by 10 pixels in total, 100 pixels. That's a 100-dimensional space. You need 10 to the 100 by basis functions. Now, in the entire observable universe, you have just 10 to the 80 number of atoms. That's all. In the entire observable universe, and it's very large. So that tells you need more basis functions than there are atoms in the universe. The number of computations is just insanely large. So the curse of dimensionality. So we can't use these linear models to fit real-world data that has very high dimensionality. So manually designing or pre-allocating fixed basis functions becomes completely intractable for high-dimensional data. We need a different kind of solution, all right? And what neural networks do is they resolve this limitation by making basis functions adaptive. So there are no fixed basis functions when it comes to neural networks. It's very adaptive. It fits itself to the data and decides what basis functions are required, all right? Parameters defining the basis functions are learned by the model. Each basis function, phi j of x, is parameterized by its own internal weights and bias. So the basis functions look like this. There is a linear combination that you do. You add a bias, and then you pass that through some function. All right, some nonlinear function, I should say. This is what introduces nonlinearity in the neural network. That function, sigma, is often referred to as an activation function in neural networks. All right. So the data itself determines the most optimal features to extract in your model. All right. So some historical context. So in 1943, a bunch of researchers introduced a highly simplified mathematical abstraction of the biological brain cell. And this is how it looked like, right? The idea in the brain is that, each neuron receives some electrical signal. You know that your body is basically electricity, right? Yeah. So it receives some electrical signals through the dendrites, and then if the total signal exceeds some threshold, then then an impulse is fired down the neuron or down the axons, if you remember these things from biology. Yeah. And what that model basically, their model basically did is it took a bunch of binary inputs. Binary in the sense that they're either zeros or ones. It sums them and then checks if the sum is greater than some threshold. So you can represent that mathematically as this. It's either 1 or 0. And that is if the summation of those elements is greater than some threshold theta, and then 0 otherwise. All right. But the problem is, even though it's a mathematical model, it really lacks the mechanism to learn. And so it's basically useless. It's a convenient representation, but totally useless in the practical world. And then you had Rosenblatt's perceptron in 1958. This researcher introduced adjustable weights. So basically, this is like you can think of this as one of the earliest almost neural networks, so to speak, right? And it basically forms a linear combination of real inputs. So you already know that this is just a linear combination plus a bias, right? Because this W transpose X, that's a dot product. A dot product simply means you're doing a linear combination of elements, all right? So it adds a bias and then passes the result through a rigid step function. You know what a step function is? A step function takes some fixed value after a certain point, okay? Like, say when some time t is greater than or equal to 0, the value becomes 1 or it becomes 2 or something like that. It's a fixed step function, all right? So f of a is +1 if a is greater than or equal to 0, and -1 if a is less than 0. So just a step function. Then he also developed a learning algorithm, basically adjusting the weights based on errors. Perform a linear combination, make a prediction, and then if there is an error, adjust the weights. Basically, really the fundamentals of our neural network works today. Okay. If a training example is misclassified, the weights are adjusted in the direction of the error. All right. And then a bunch of mathematicians decided to write a critique of that model, of that perceptron. All right. In 1969, some two researchers called Minsky and Papert published a rigorous mathematical critique of the perceptron. And basically what they said is that this perceptron, it looks clever, but it is fundamentally a linear classifier. So we still have the same problem of linearity again. It is entirely incapable of solving problems where classes are not linearly separable. I think 2 days ago, Emerson talked about this exclusive all problem, where basically you have these various, you have this XOR function, where if it's 0, 0 or 1, 1, the output is a 0, and otherwise it's a 1. You know what's interesting about this is it looks very simple, but if you plot this on, if you plot this here, right, is you have this and this. So you have 1, 1 here and 0, 0 here. So these two belong to the same class, and these two belong to the same class. There's no way to linearly separate them. Absolutely no way using a single line. All right. So that perceptron fails on a simple task like the XOR problem. All right. Okay. So no straight can separate zeros from ones in a 2D plane. Okay. So they noted that adding hidden layers could solve this, but argued that there was no computationally efficient way to train them. So they recognized that adding layers, introducing complexity into the perceptron would likely solve that problem, but this is 1969. We didn't have the computation to do that, all right? Right? So, and this resulted in what is historically known as the first AI winter. So for a long time, beyond 1969 up to the 80s, there was basically zero funding for AI research, all right? And that's known as an AI winter. And then years later, in the 80s, the field was revitalized by replacing rigid discontinuous functions with continuous differentiable activation functions. So by introducing activation functions, that sigma that we saw earlier, essentially changes everything, all right? The step functions have a derivative of 0 everywhere except at the undefined boundary. You know, that step jump from -1 to 1, mathematically it is not differentiable. It is known as a discontinuity in calculus, right? You cannot differentiate at that point. So that means at that point, you cannot take a gradient, and therefore you have no way of updating your weights because you don't know in what direction to update your weights, right? So, but when you take a smooth function like a logistic sigmoid, sigma of A is equals to 1 over 1 plus the number E to negative A, this is the sigmoid function which we say it squishes all values to between 0 and 1. And it's a curve, it's fully differentiable in its domain, okay? So it makes the model fully differentiable, which means you can take the partial derivative of y with respect to the weights, right? Can be computed via the chain rule, basically. This enables backpropagation, which is an important algorithm that makes all neural networks that we know learn. So, multilayer perceptron. Multilayer perceptron is like a basic neural network with a bunch of layers. So we have an input layer, a hidden layer, and an output layer. The hidden, you could have more than one hidden layer, basically. And you have basically, it's called a feed-forward neural network because you have multiple layers of computational units that allows information to flow strictly in one direction. So it's like a forward pass. You make information flow in a single direction. And we call it feed-forward to differentiate it from recurrent neural networks where there are feedback loops, all right? So information flows in one direction and it never comes back. There is no feedback loop. Right? The output of any given layer cannot loop back to influence itself or any preceding layer. Okay? And the other thing is that mathematically, this feed-forward network or multilayer perceptron can be formalized as a directed acyclic graph. All right, so you might not be familiar with graphs, but basically a graph is a collection of nodes and edges where the nodes are connected together by edges. And then the directed here simply means that each edge has a specific direction, indicating that node I passes its output value to node J, never backwards. So it's a forward flow and there's no feedback. And it's acyclic in the sense that it's not cyclic. There are no paths or closed loops that allow an information signal to travel from a node and eventually return to it. Okay. Okay. So yeah, I guess maybe it might be useful to see what a graph is. All right. So basically, this is what we mean by a graph. So something like this. These are nodes. And at each node, there's a computation that is happening. And these are basically weights. These weights say, for example, how much, by what value, a scalar value, should the resulting output of this node be multiplied by. That's a weight. All right, so if the weight here is 0.5, it simply means the output of this node, which is some computation, the result of some computation, should be multiplied by 0.5 before being passed to the next node. All right. So yeah, so that's a graph. Okay. So when we view this feed-forward network as a directed acyclic graph, it becomes very useful because today, even though we'll be discussing the backpropagation algorithm, really rarely will you ever have to write your own backpropagation algorithm unless you're curious and just want to learn. In modern deep learning or machine learning libraries, all that has been sorted out for you because of this graph representation using libraries known as automatic differentiation libraries. PyTorch is a very good example. TensorFlow also has automatic differentiation, so you never have to do all this calculus on your own. Okay, so in a multi-layer perceptron, you have an input layer. We often refer to an input layer, but really, sometimes it's convenient to think of it as no layer at all because it's just the inputs themselves as a vector. No mathematical transformations there, just the raw environment feature vector X. All right. Then you have hidden layers, which are not directly observed in the training set. They extract increasingly abstract features from representations provided by previous layers. And then the output layer transforms the final hidden representations into the prediction y hat. Remember that in machine learning, our goal is to learn y hat. All right? Y hat is the function that we are, or rather f hat of x is the function that we are trying, the approximate function that we are trying to learn. And the output of f hat is basically y hat, the output feature vector. All right. So this is what a multi-layer perceptron looks like. So you have the input layer, which contains the inputs from x0 all the way to xd. We said the input vector x is d-dimensional. So you have a bunch of d. If d is 3, this should be 3 edges, 3 nodes rather. All right, and then you have these hidden layers. The hidden layer in this case is just one. Let's say there are m of them. And so at each node, there's a computation that is performed. All right, there's a computation that is performed. And then that computation is weighed or multiplied by a scalar value WMD. This is a weight. So MD simply means, basically, that subscript simply means it's the weight that is connecting node D to node M here. So we're representing it as a graph, but really, as an engineer, think of these computations that are happening. Okay, so there's a function there, and then, yeah, there. All right, so, and then you have your outputs here. The information is flowing like that. It's flowing like that. Right. So this is a classic. You can think of it as a 2-layer multi-layer perceptron, or as a 3-layer. 3-layer if you count the input as a layer. Again, the source is from that book, Pattern Recognition and Machine Learning. All right. The individual processing node, which is the neuron, performs 2 mathematical transformations on its inputs. So that single node, that single circle that we saw there, we said, think of it as a bunch of computations that are happening. What computations are happening? Number one, a linear combination. There are certain linearity aspects, linear aspects in the multi-layer perceptron. A linear combination, that W transpose X plus B. That's a linear combination. And then a nonlinear activation. That function that we saw earlier as sigma, activation function. All right. It's called an activation function because it determines whether the neuron becomes active or inactive. All right. If the value is greater than some threshold, the neuron can be considered to be off or on. All right. So let a neuron receive an input feature vector x. Say that our input is the feature vector x, which is d-dimensional. The unit, by the unit here, we really mean the neuron. The neuron computes a weight as a scalar bias b, activation. The linear combination wi, xi. Wi's are the weights. You can think of this as a summation, but of course, when we are doing computations like this in a computer, rather than representing like this as a summation, represent it as a dot product of the weight, the weight vector and the feature and the input vector, wt x plus p. This is a linear combination. Or rather, let me just refer to this as a linear operation. This is a linear operation. Okay? So the output is the pre-activation value A. This value A is what we are going to pass into our activation function. Our activation function sigma, where W determines the orientation of the neuron's decisions plane. I mean, we're just calling this a linear combination. That's what we're saying. B shifts the activation threshold away from the origin. B is basically the intercept. And WT sort of gives you the gradient, if you like, if you think of this as a straight line, okay? And then we convert that pre-activation value into an adaptive feature, okay? It is passed through a nonlinear activation function to yield the post-activation value. So you need to think of this, there's a pre-activation value and there's a post-activation value. The pre-activation value is the result of a linear operation. The post-activation value is the result of a nonlinear operation, Z. So this sigma function is a nonlinear function which we are referring to as an activation function. And there are various activation functions that we'll look at. And for this to be of any practical use in our algorithm, the function sigma has to be continuous and differentiable throughout its domain to permit gradient-based learning. Because if it's fully differentiable, we can compute the gradients, and the gradients, as we already saw, are the things that help us to see in which direction to push our weights. Should we push our weights forward or should we push them backwards? Right. Various activation functions. The sigmoid is the logistic sigmoid function which squashes input into a bounded range between 0 and 1. All right. So the mathematical property is that it has a very compact derivative. Now, you can see that this function is an exponential function. You can see it as there is an exponential within it. You know, performing derivatives of exponentials from your calculus class, you know it's like one of the easiest things that you can ever do. So it has a very compact derivative. So the derivative of the sigmoid function is the sigmoid function itself multiplied by the difference between 1 and the sigmoid function. All right. So it's a very convenient activation function. It has a limitation though. When A is very large or very small, the curve flattens. All right. So we said that value, you know, it takes values between 0 and 1. All right. So when it's very large, that means, you know, when A is very large, that means when it's close to 1, or when it's very close, when it's very small, close to 0, the curve flattens, as we already saw. All right. The gradient sigma prime approaches 0, leading to the vanishing gradient problem. I mean, just look at this function. Look at this function by this derivative here. What happens when sigma of A is 1? When sigma is 1, what is inside the second bracket is 1 minus 1, isn't it? If it is 1 minus 1, that is 0. And this value is 0. But what happens again when it is 0, or when it's very close to 0? This value here, which we are pre-multiplying by what is inside the parentheses, is effectively a 0. So when it's very large or very small, then this value disappears. Your gradients become effectively very, very close to 0. That is known as a gradient. All right. Okay, another one is the hyperbolic tangent. It is another sort of function with exponentials. You can see how it can be written here. But this one, the difference between this and the sigmoid function is the sigmoid function forces values to the range 0 to 1. This one, hyperbolic tangent, forces values to the range -1 to 1. So you can think of the value at 0 as its average. It is zero-centered. Outputs have an expected value close to 0 when inputs are symmetrically distributed, which stabilizes our optimization. All right. But the limitation also is like the sigmoid function, it still suffers from saturation at extreme values of A. All right. Another common one that is used today is something known as ReLU, which is the rectified linear unit. The rectified linear unit is it's a nonlinear function with linear portions. I like to think of it like that. F of A is a max of 0 and A. So if A is 2, then that means it is a max of 0 and 2, which would be 2. We'll see how the curve looks like. The advantage is that for any positive pre-activation, A is greater than 0, the derivative is exactly 1 because it's a straight line. All right. This completely eliminates vanishing gradients for positive paths. Okay, but it's extremely cheap to compute because you don't have to calculate the gradient. You know it's 1. All right. The limitation is, this has a limitation that is often described as the dying ReLU problem. That for A is less than 0, the output and derivative are exactly 0. All right. So if you plot that rectified linear unit function, this is how it looks like. All right. So it looks like this. All right. That when A is greater than 0, it's a straight line with a gradient of 1. But when it's less than 0, it's a straight line. So it's a nonlinear function. But you can see that straight line there simply means that the gradient here is 1, but the gradient here is 0. So if the neuron always receives negative inputs, its gradient stays at 0 forever. That's a problem. If your gradients are staying at 0 forever, you're not learning anything. It's a dead neuron. Right? That's why it's called a dying ReLU problem. Another one is something known as a leaky ReLU, and another one called GELU, which is just to mitigate that dying ReLU problem. All right. This one introduces a small constant slope, a very small slope, like 0.01 when A is greater than 0. So it's like, rather than having a straight line there, you still have the straight line, but with some non-zero gradient. All right, and then another one called Gaussian error linear unit, used in the transformers and deep learning, like deep multilayer perceptrons, weights inputs by a standard normal CDF. So these ones, what they do is they create a smooth approximation of ReLU, preserving slight curvature for negative values, so that we do not have the zero gradients. Okay, so this is how those activation functions look like. This is the sigmoid function. It forces values to between. No, this is not the sigmoid. This is the hyperbolic tangent. Values between -1 and 1. There's also another one called the hard tangent, soft plus. Some of these are rarely used. Never even heard of them. ReLU looks like before. This is the leaky ReLU. So you have a small positive gradient below 0 and a gradient when A is greater than 0. And this is the absolute value. That means you're taking the absolute values, basically. Okay. All right. Let's look at some matrices, right? So the multilayer perceptron that we've looked at can be conveniently represented using matrices. And what that does is it helps us to avoid scalar iterations. We aggregate all these individual neurons into a single matrix so that we can take advantages of linear algebra. One of the advantages of linear algebra is vectorization, something known as vectorization, where you don't need to write any for loops. You just put things into vectors and matrices and you multiply them together. Takes advantage of the efficient computational efficiency of working with vectors and matrices. For a single hidden layer of m units and input x, which is, so basically this means it's a d-dimensional input, the one we've been talking about. We collect all the weights into a matrix W1 of size M by D. Oh, okay, I guess maybe it would be nice to just draw it here. What I want to do is to just explain briefly why we can leverage matrices. If you draw a single neuron here, right? Let's say this is one of the hidden layers, and it's receiving inputs from various other various neurons. Let's say these neurons are the input layer. We don't need these are just the input layer. We don't need to think of them as neurons because they're just input. So this neuron here, let's call this X1, X2, X3, X4. And then there are weights. They are weighted by some values. Let's call this W1, W2, W3, W4. So we see the value that this receives here, all right? Let's call this A1. So A1 is going to be W1, X1, plus all the way to W4, X4. We've said this can be written as a vector W1, W2, W3, W4 multiplied by X1, X2, X3, X4, right, is equals to, you can see this is a vector which has been written as a row vector. So we can call it W transpose, all right? And this one is, we can call it now X, W transpose. But now, this is for a single neuron, isn't it? Now imagine you had very many other neurons here. Now when you have many other neurons here, you're going to have, every single one of these neurons is going to be receiving inputs from the previous layer. So there'll be that. This one will also go down there, and will also go down there. The same case for this. It's going to go there, it's going to go there, it's going to go there as well. And same case for this. You're going to have connection to every single neuron. Oh, oops. No, that's already there. That. What happens to this? What happens to a weight vector? And remember, each of these connection is a weight. It's a weight. It's a weight, it's a weight, it's a weight. For every single one of these neurons, there exists such an operation. Okay? There exists such an operation. Let's call this maybe, okay, A2, A3, A4. Yeah? All these are individual neurons. And each one of them has an operation like this. And what you notice about this operation is that what is common, maybe let's call this W. Let's call this, it's a vector, all right? W1, vector 1 that contains the weights associated with the first input feature, input value, X. And then there'll be W2, X, W3, X, W4, X. Doing these repeated operations, all these vector products, all these dot products, all of which include a multiplication by the input X, is a lot of repetition. Don't you agree? It's repetition because you're basically doing this multiplication of this input by a weight vector. It is more convenient mathematically that you collect each of these and put them into a single matrix. All right? Because basically we know that we know that vectors and matrices are essentially related. In fact, it's very common in linear algebra to visualize a matrix as a bunch of columns that are vectors. So what we do is we collect all these here and we put them into a single matrix here of size m by d. Why m by d? Because we know for sure how many, all these here, this m is basically the number of weights. So W1, W3, W4, all that. In our case here, W4 would be, like 4 would be m. So this would be 4 by d. But if you have a total number of your, if the number of your input, if the number of the weights is m, then you can collect this into a matrix of size m by d. This is a very convenient representation. So what this is telling us is that all these things, it looks complex, all those connections. But hey, what we are saying is that is just a simple matrix vector product. All right, it's a matrix vector product, which we are so used to working with from your math class or something like that. Right, and then collect the biases. Now, okay, what I didn't mention here is that you have W1 x1 all the way plus W4 x4, but there's another element that you add, a bias. All right, there's a bias. So that means you can collect all those biases related to all these operations into a single vector. The bias was a scalar, but when you collect many biases together, you can form a vector. So we moved our weights from a vector to a matrix, and we moved our biases from being scalars to being a vector. We collected them all together. All right. So the vector of preactivations A, which is m-dimensional. It's m-dimensional because we have m neurons. So that means then A becomes W, which is no longer a vector, but rather a matrix, multiplied by X, which is the same input vector, plus B now. B is no longer a scalar, it's a vector because we've collected our biases into a vector. All right. So now A is a vector of preactivations. This A here is what I was writing there as A1, A2, A3, A4. Preactivations A, like that. And then after you've collected your preactivations together, you can now pass them through a what? An activation function. And because every single one of these neurons has the same activation function, the activation functions are the same. You don't have a different activation function for various neurons. That means you can collect all of them into a single a vector as you've done before, them through an activation function. The activation function now is working or operating not on a scalar, but on a vector. All right. Again, it's a vectorized operation. Okay. So this Z now is a post-activation value, which is the hidden output vector Z, also an element of Rm. Simply means it is m-dimensional, that language there. So the hidden representation is passed to the output layer, okay? So if we further draw our network here, we'll have the output layer, all right, which has k units. In general, yeah, k units with a weight matrix M, with a weight matrix W2. So you can imagine, maybe I guess it's just nice to explain like this, that you see all these connections here, all those connections we are saying, we can summarize them as the weight matrix 1, okay? But if we further connect this to the let's say it's a single hidden layer like that, and we say, let's say the output layer is going to be 3 neurons like that, we make more connections again, more connections like that. All right? These weights again, all those weights, as in this case, we can also summarize them as another weight matrix. So every single layer, every pair of layers in a neural network, their weights can be conveniently summarized as a weight matrix. So these can also be conveniently summarized as another weight matrix. So basically, and so on and so forth. Even if you had a very deep layer, you are a very deep neural network with further connections again. Make these additional connections again like that, and you have another weight matrix, and so on and so forth. Right? So you can have as many layers as possible as is necessary for the task that you're doing. But in the end, we are saying you can always represent this as a linear operation, which is W2, in this case, the weight matrix, and bias vector B. B2 in this case, because you have more biases here and more biases for every layer that you create. So A is a pre-activation for every layer, and Z is a post-activation for every layer. All right. So what essentially is passed from this layer to this layer is Z, not A, because A, what arrives from this layer is passed through an activation and then passed into the next layer. So there are two things that you need to keep in mind as we discuss these neural networks, that there's a post-activation value and a pre-activation value. You're always interested very much in the post-activation value, because that is what you pass to the next, layer. And it's important to know the dimensions of your matrices. The dimension for your matrices will always be the number of units in the next layer by the number of units in the current layer. So if your next layer has 2 neurons and the current layer has 3 neurons, then your weight matrix is going to be 2 by 3, and so on and so forth. So you have to track the dimensionality of your matrices if you are thinking about this and how it's happening conceptually. Okay, and the final row predictions y hat, which is k-dimensional, as we've said, is basically some final function some final activation function that is in the output layer to activate these values, so to speak. All right. What we want to do is to generalize this to L layers, whatever number of layers we have. For any intermediate hidden layer L, okay, which is from 1 to L, not 0, because 0 is our first layer. The operations scale recursively. So you have A for layer L, the pre-activation value for layer L is this linear operation here, which is WL, the weight matrix, multiplied by Z, the post-activation value from the previous layer. The inputs sent from the previous layer, plus the bias vector, again, from the current layer. So you see, we are always operating on the inputs from the previous that are sent from the previous layer. And then the post-activation value is applying the activation function in the current layer to the pre-activation value of the current layer. Where Z0, of course Z0 would be X. Z0 would be X because it is what is coming as inputs, okay? And Y is ZL. I mean, this is just convenient, mathematical language, but all we are saying is that the output is basically the activated value of the last layer, right? When we can write this completely as a nested functional composition. It's a nested function where you have W1X as your input plus B, all right? And then you activate that and so on and so forth. You perform operations until you get to layer L, where you perform some function, some activated function in the final. We are representing this as F because the final layer, you use some different activation function depending on what your task is. There are different activation functions for your final layer depending on what your task is. So the choice of the final layer activation function F, which is operating on these pre-activation value of the last layer, AL, is dictated entirely by the statistical nature of the target variables. If you're interested in continuous target variables, you use linear activation. Basically, you take the inputs as they are and you multiply by 1. That means you do nothing to them. All right, for continuous target variables, if you're performing a regression operation, in short. But if you're performing a binary classification task, the activation function uses a sigmoid activation. Why use a sigmoid activation? Because we know a sigmoid activation forces values to between 0 and 1. So what it's going to do, the values are going to take the value either 0 and 1, depending on whether it is greater than, the threshold, which is 0.5, essentially. Okay? And for multi-class activation tasks, use a softmax activation function. We'll see what a softmax activation function looks like. Softmax simply says if you have 10 output neurons, then the outputs of those 10 active neurons should be such that their sum is 1. That's what a softmax means. Okay. So for a continuous and constrained target, then y hat is the same as AL. So the activation is simply multiplying by 1 or simply doing nothing. Okay. For binary classification, sigmoid. Perform a sigmoid operation. That's what it means. Okay? And in the case of multi-class, we said use a softmax function. This is what it looks like. It means you take the pre-activation values and then perform. I don't think this is. Is this right? Oh yeah, this is right. Yes. Okay. So you take them and then exponentiate them and then divide by their sum. Simply what this is saying, if you're dividing certain values by their total sum, what it's simply saying is that you're performing a weighted average and forcing the values such that their sum is equal to 1. So if there are 3 values, one might take the value 0.6 and the other one takes 0.3 and the other one 0.1. The total sum is 1. And that 0.6, 0.3, and 0.1 are really exponentiated values. You've taken the outputs of the last layer and exponentiated them. Okay? So you exponentiate unconstrained real values that are known as logits, whatever, to ensure positivity. So even if the value is -1, for example, when you exponentiate it, e to the -1 is always a positive. As in, e to any value is always a positive. It's always a positive value. So the idea is to turn them into real values, into positive values rather. And you normalize by dividing by the sum of all exponentiated values. Okay. So for softmax outputs, this is really the statistical interpretation. All right. So it maps into a multinomial or categorical distribution over the classes. And it is written like this, that it's really it's some product operation. And this looks complicated here, that the probability of some true vector given x, the inputs, and the weights is this product here. From k is equals to 1 all the way to k, which is really the dimensionality of your output, and it's the product of the various values raised to the power tk. But here's the thing. Tk is really a one-hot vector. Here's what I mean. A one-hot vector simply means if your vector is d-dimensional, one element is going to be 1, and the other elements, all of them, are going to be 0. Why are we saying it's a one-hot vector? Because look at it this way. If you're making a prediction of a multinomial, if you're making a prediction in a case where you have only 3 classes, let's say you have 3, you're making a prediction of 3 classes, right? 3 classes. There's only one class that is the correct one because you're making a prediction, isn't it? Let's say you're classifying images. You're classifying images and there are 3 possible outputs. That it can be either a cat, a dog, or a bird. 3 classes. When you feed an image to the neural network, you know that there's only one correct class for that image, isn't it? It cannot be an image that you classify as it's both a bird and a cat. It's not possible. So only one class is going to be right. So it's going to be 1, 0, 0, or 0, 1, 0, or 0, 0, 1. This is what you want your neural network to predict. The neural network should either predict that it's 1, 0, 0, or 0, 1, 0, or 0, 0, or 0, 0, 1. This is what I am referring to as a one-hot vector. Only one class is right. And you are raising this value yk, which is your output, to tk. So in this case, 1, 0, 0, t1 is 1, t0, t1 is 1, t2 is 0, and t3 is 0. So in this case here, if you're performing this product from k is equals to 1 to k is equals to k, the output here is going to be such that you're going to be, and when you raise anything to power 0, what happens? It's always 1, isn't it? So the product, if we draw out this and you know, write this as a product, k is equals to 1 to k is equals to k, yj, all right? All right. So basically what we are saying is, let's say that you're given a target class j. Your target class is j, where tj is equals to 1, and t, when k is not equal to j, is 0. That's exactly what we are saying here, that it's a one-hot vector. This product is going to look like this. It's going to be yj raised to power 1, because it's you know, tj in this case is 1, times everything else whenever k is not equal to j. Yk in that case would be raised to power tk not equal to j is what? Is equals to 0. So it's going to be yk raised to power 0, which is this product here. It's basically yj times everything else, which is a 1. So it's essentially, this is what it's saying, that the probability of the observed class is exactly the model's predicted probability of that label. Are you seeing? The probability of the observed class. Let's say you have 3 classes: cat, dog, and bird. The probability, according to the model, the probability of a bird, when you feed a certain input x, let's say you feed an image, the probability that that image is a bird is exactly what the model is going to predict. That's all it's saying. It looks very sophisticated, but I guess mathematicians sometimes they just like to flex. Like write very complex functions to scare us, but really the interpretation is a very basic one. That if you feed an input into that model, and the model predicts that this image is 0.9 probability a dog, and that is all it's saying, that the probability of a dog is what? Is 0.9. That's all it's saying. Okay. So anyway, that's all. That's the softmax function. That's what it's saying. Now, universal approximation theorem. There's a theorem that apparently covers neural networks, right? So this is what it says here. This is from 1989 and 1991. A bunch of researchers who came up with this, that a feed-forward neural network with a single hidden layer. This one, assuming this, just assume this layer doesn't exist. Just this feed-forward neural network here. An input layer, a hidden layer, and an output layer. That a feed-forward neural network with a single hidden layer like that, containing a finite number of neurons, obviously this number is finite, can approximate any continuous function on a compact subset of Rd to any desired degree of accuracy, provided the activation function is continuous, bounded, and nonlinear. This is what it's saying. All right. If we don't even go into the details of this theorem, this is what it's saying. That this is a highly flexible function. That is what it's saying. It's a highly flexible function. Do you want to approximate a sinusoid? Oh yeah, you can approximate a sinusoid. Do you want to approximate a polynomial? Oh yes, you can approximate a polynomial. All right. That is what this theorem is saying. All right. On a compact subset of Rd, all right? So as long as you're dealing with an input that is d-dimensional or less than d-dimensional, you can do that with this feed-forward neural neural network. And indeed, you can do an experiment and see whether you can model a polynomial with such a neural network, and you'll be see. Of course, the theorem doesn't tell you how much training you need to do on the neural network to approximate. It just tells you, oh yes, it's possible. Mathematically, it's possible, all right? It guarantees that a shallow network can theoretically represent any smooth mapping. Even if you want to represent, even if you want to approximate a polynomial of order 20, oh yes, you can. All right, as long as you choose, you choose an input that is either 20 or less in terms of its inputs. Okay, okay. So it turns out that also multilayer perceptrons, for all the nice things that we've said about them today, also have the curse of dimensionality. All right. If a single hidden layer is theoretically sufficient, why should we use deep neural network? All right. So the theorem that we just came across is really just an existence proof. The theorem guarantees that a network exists, okay, but does not specify the size or ensure gradient descent can find it. All right. And the other thing is approximating complex, highly oscillating functions can require an exponentially large number of hidden units. All right. So some functions will require you to just have a ridiculous number of hidden units. All right. Okay. But by number of hidden units, we really mean in that single hidden layer, how many neurons do you need? Okay, and the other thing also why we use deep networks today, you hear a lot about deep learning, is that because of this thing here, hierarchical feature extraction. That as you go down, as you go through the network from left to right like that, each of these layers is extracting certain features. So the deeper the network, the more the capabilities of the network in terms of its ability to extract these features. So early layers might extract simple edges in the case of image processing. Later layers might compose them into shapes and then complex objects. And deep network use far fewer parameters than shallow counterparts. Oh yes, it's possible. You can have a shallow network but has a ridiculously large number of hidden units. That will be a network that has a very large number of parameters. Anyway, loss functions. Suppose we have a data set that has n independent and identically distributed observations x. Okay, so x is like a matrix, isn't it? Because you can see that inside it we have these vectors with target labels t. All right, we use different loss functions to compute the error in the network's predictions depending on the task. You can use neural networks to perform a wide variety of tasks. You can do regression with neural networks, you can do classification with neural networks. Okay? So for regression, we use the sum of squares error function. Sum of squares, we've come across this very many times, isn't it? In our linear regression class, I talked about it. This is the target value, and this is the predicted value. You find the difference, and then you square it. You know, I'm representing this as a norm because really it is inconsequential whether you represent it as a norm or you just find the difference and then square it. If you square it without finding the norm, the value is the same as finding the difference and squaring it, because squaring it really does away with a negative value. Okay. For binary classification, we minimize the negative log likelihood here, as you can see. Basically, it's saying you take the target value multiplied by the logarithm of the predicted value plus 1 minus the target value. This is binary. If it's binary, what this is telling you is that at the end of the day, when you compute this value, one of these terms is going to be off, isn't it? Because if Tn, which is an element of this set here, 0 or 1, if Tn is 0, then this value is off. And if Tn is 1, then this value is off. So it's going to be really computing one of these values as opposed to both. Okay? For multi-class classification, with mutually exclusive classes, I already spoke about it, one hot target. Your target is going to be one hot, something like this, 1000010 001. All right. We use a softmax. We use a softmax output. Again, softmax is an exponential. You can take the logarithm, and this is how it's going to look like. Okay. Okay. The error surface. It's always nice to know when you're dealing with neural networks what your error surface is going to look like, because when you know, when you have a knowledge of your the error surface is going to look like, you know what the optimization process is going to look like as well. So an error surface spans a high dimensional space of W parameters. So we've been talking about error surfaces here, even from our linear regression class. You know, we've drawn 2D images or 3-dimensional images to represent the error surface. But in reality, your error surface is much, much more complex. It is high dimensional. You might have a neural network. You guys know that sometimes you're dealing with neural networks that have billions of parameters. So that means the error surface is of what dimensionality? Billions in dimensionality. And we need to work with that. And so unlike linear models where the error surface is a convex paraboloid, it's basically a parabola in higher dimensional space. MLPs yield convex landscapes. You remember what I said non-convex is? Non-convex means you have more than one local, you have more than one local minimum. If you have more than one local minimum, that means you don't know where the global minimum is going to be. And you might perform an optimization, and if your optimization algorithm cannot deal with that non-convexity, it means you might end up with a local minimum as opposed to global minimum, which is what you're interested in. So they yield non-convex landscapes which have a global minima, an absolute lowest possible error value. They also have local minima where the error is lower than the immediate neighborhood but higher than the global minimum. And saddle points as well. You remember what a saddle point is? It's a point of inflection. All right. So the local geometry of the error surface, and this is information anyway, I am giving it to you, it's just for your general knowledge. The local geometry of the error surface is analyzed using eigenvalues. You know, you guys have probably studied eigenvalues in your calculus class or something like that, or linear algebra. Eigenvalues of the Hessian matrix function. So when you get your error function, which is really, the error function is a function of the weights. The Hessian matrix simply means you're taking various second derivatives, all right? You're taking various second, it's like, you know, when you first studied optimization, let's say in high school, and you did your differentiation and you wanted to understand whether the value that you've computed is a maximum or a minimum, what were you doing? You were taking a second derivative, isn't it? And determining whether is the second derivative negative, is it positive, or is it 0? If it is 0, you know this one is a saddle point. All right? If it's negative or positive, then you know it's either a minima or a maxima. It's the same thing, except in this case, because now we are more sophisticated in our understanding of math, we can take those second derivatives, all right? And you're taking second derivatives, and your Hessian matrix here is going to be very large because you're taking the second derivative of your error function with respect to billions of weights, or millions of weights, or hundreds of thousands of weights. So you're taking second derivative of the error function with respect to weight 1, with respect to weight 2, with respect to weight 3, with respect to weight 4, all the way to hundreds of thousands. And you're not just doing that. You're also taking the second derivative with respect to various combinations of weights, you know, with respect to weight 1 and weight 2, or weight 1 and weight 2 and weight 3. All right, all that, if you do those second derivatives together and you collect them nicely into a nice matrix, that matrix is what we are referring to as a Hessian matrix. And if we can then compute the eigenvalues of that Hessian matrix, which is going to be very large, we can understand whether the error surface that we are dealing with is convex or it's non-convex, and whether we are heading to a local minimum or or a global minimum. All right. Maybe if you become a graduate student one day, you might study optimization and look at Hessian matrices. Hessian matrices are just a nice way to collect second derivatives. It's a sophisticated name, but that's all that it's saying. Okay? If all eigenvalues of the Hessian matrix are strictly positive, it's a local minimum. If all eigenvalues of H are strictly negative, this strictly positive should be a global minimum. Yeah? Yeah. And if eigenvalues are strictly negative, that should be a local minimum. Or I'm confusing one of those two. I'm not sure which is which. But if there's a mix of both positive and negative eigenvalues, then it's a saddle point. And now your optimization process when you're dealing with neural networks has to deal with that. It has to deal with these large Hessian matrices and decide for itself whether am I dealing with a global minimum here or it's a local minimum. And this is what your error surface would look like in 3 dimensions with respect to weight 2 and weight 1. And this is your error surface. You're differentiating and then ending up with a Hessian matrix. In this case would be a very small matrix. All right. Your matrix here would be literally 2 by 2. It would be a 2 by 2 matrix because we have how many weights? 2 weights. And then you can decide whether you have a global minimum or a local minimum. All right. Okay. Okay. In the past, early literature on machine learning was really focusing on whether are we getting trapped in poor local minimum. But in modern networks, where your weight matrix is spanning millions of dimensions, a true local minimum requires the slope to curve upward in every single one of the W dimensions simultaneously. And the probability of that is extremely low. Because remember, how do we update our weights? You remember when we studied linear regression, we looked at gradient descent. How are we updating our weights? We are updating our weights by computing the gradient and then going in the opposite direction of the gradient. The gradient is always going where? Up. So we go in the opposite direction because we are going where? Down towards the global minimum. So the probability of that is exceptionally low because you're dealing with billions of dimensions or millions of dimensions. Yeah. So the takeaway is that the vast majority of critical points here are going to be saddle points. So you're going to have points that, they're just saddle points, giving you a mixture of positive and negative eigenvalues. And optimizers must traverse these flat regions, saddle points, efficiently without stalling. So it has to go. Look for finding saddle points, ignoring them, because it's looking for what? Looking for the global minimum. Okay. I'll go through these ones very quickly. Gradient descent algorithms, your error surface looks like that. This is a valley, and it's going to be jumping up and down, the error surface. Why is it jumping up and down? All right. Schematic of fixed step gradient descent on an error surface with highly different curvatures, a long valley shown by ellipses, this one here. The local gradient usually doesn't point to minimum, so steps can oscillate across the valley and make progress towards the minimum. Yeah, these are your eigenvectors here. So you're going to be jumping up and down the valley because you are going towards you're looking for the global minimum. So in the case of batch gradient descent, I may have mentioned this even though the notation here is different, is we are saying this is how we are updating our weights. You get your weight vector and basically subtract the gradient multiplied by some learning rate. You remember this value here, eta, the learning rate. The learning rate tells you how fast or how slowly to go down the hill. You see, when you see an equation like this, don't get scared. Just ask yourself, what are all these individual elements actually representing? Because you see here, this is the gradient of this value here. That's the gradient of the what? Of the error surface multiplied by the learning rate. Okay. All right. And when n is greater than 0, that is the learning rate, and t is the iteration, tau is the iteration index. If the data set contains millions of samples, every sample for a single update, tracking every single sample for a single update is going to be computationally slow. Yeah, computationally slow, basically. because you're doing this summation from n is equals to 1 to n. So that means you're computing, this update is a very long loop, all right? A very long loop. You can avoid that because it's going to be computationally slow and intensive, right? Stochastic gradient descent. Stochastic gradient descent is different because even though this looks the same because you're updating the weights in the same, it's saying rather than doing this for all individual values, we're saying we are going to update our weights every time we see an input. That's what it's saying here. Every time we see an input, just one input, we compute and update our weights. So you're updating your weights more quickly. You're getting it. As opposed to the other one where you're saying, I want to collect for me all the inputs. Once I have all the inputs, now I can compute my weights. Doing that summation is going to take very long. So this one says, every time you see an input, perform an update on the weights. Stochastic gradient descent. The advantage is that the updates are quick and data can be processed on the fly, as opposed to waiting for all the inputs first. But the problem is you're working with a single sample. The problem with a single sample is that the single sample is never a statistical, or it's never a statistical representation of the whole. So that means if you perform an update on the single one, you might really be going down when you shouldn't be going down. So what you end up with is optimization path is going to fluctuate significantly. Those bounces that we are talking about, going up and down. Minibat gradient, stochastic gradient descent is simply saying, rather than waiting for the whole value or taking a single value like in stochastic gradient descent, just take a batch, a small batch. Maybe you have 1 million inputs. Instead of taking all the 1 million inputs to update your weights, just take a batch of them, like maybe 30. If you take a small batch, it means it's still going to oscillate, but not as much as in the stochastic gradient approach. So you're taking partitions, the data set subsets B containing B samples, 32, 64, 256. It's always common to use powers of 2. So this is what it's saying. Essentially, this is what it's saying. So the learning rate is going to be divided by the number of samples. So it reduces the noise compared to stochastic gradient descent, but it also leverages parallel hardware processing because you're taking a batch. It means you're going to be dealing with matrices. And when you're dealing with matrices, another way to represent matrices is to represent them as tensors. All right. And when you're working with tensors, it means you can put this into a GPU. If you can put them into a GPU, the computations can be very fast. Okay. Okay. Back propagation. Okay. I guess I'm bored today. So in order for us to update the weights, we already said that we need to perform a gradient. This operation here is a gradient of the error surface. We must calculate exactly how a tiny in a specific weight, Wji, impacts the total error. So you see, we have billions of weights in our model, in the model that we are training. And each one of those weights has a certain impact on the error, has a certain impact on the error surface. We need to understand how each of those weights, every single weight is affecting the error surface. That's what the computation means, isn't it? This here, by the way, this here is how we are updating our weights. Okay, so we perform that partial derivative. Why are we doing a partial derivative? Because the error surface is a function of very many weights. It's a multivariate function. That means if it's a multivariate function, it means you can leverage the skills that you got from your multivariate calculus class. Basically, backpropagation calculates these derivatives efficiently by applying the chain rule. Because we perform this derivative of the error surface with respect to the weight. But the weight is also in turn impacted by something else. The weight is a function of something else. All right. So in order for us to compute the impact of the weight on the error surface, we have to work with the chain rule. Let's see what the chain rule says. That if y depends on u and u depends on x, then the derivative of y with respect to x is really the product of the derivative of y with respect to u and the derivative of u with respect to x. That's the chain rule. You learn this in like first year. And then if x influences E through multiple independent paths, A1 and A2, then this is what the chain rule says. We can do the impact, okay? So the derivative of E with respect to x is the derivative of E with respect to x along path 1 plus the derivative of E with respect to x along path 2. And if you have in total j paths, why are we doing paths here? We are doing paths here because we see if we trace the error that we are computing here, it's affected by the various weights along different paths. So we need to know this idea of the chain rule along different paths. So along path 1, derivative with respect to A1, and then derivative of A1 with respect to x, and then A2 and A2 with respect to x. So we can do a summation. All right. Okay. Now, it's always nice that if things are complex, we can reduce their complexity first, just to understand. So we focus on a single connection path. Consider the weight Ji connecting output node I to connecting the output of node I to node J in the next layer. The sequence is there's a pre-activation. Let's go back to our pre-activation. AJ, all right? So remember, here, always nice to visualize. You have node I and node J. And we are saying that is the weight. The weight in this case is weight Ji. Okay? So there's going to be Ai and Aj, and then there's going to be a Zi and Zj there, where Z is the post-activation value. Okay? So let's just focus on that single connection. Let's see. So the pre-activation value Aj is Wji multiplied by Zi, the post-activation value from node I plus Bj, the activation. And then the activation function Zj operates on the post-activation value Aj to get Zj, okay? And then the forward flow, now you have that signal traveling, or that value traveling, that computed value traveling, signals travel forward. And you can trace this all the way down to where you finally compute your error, isn't it? So we apply the chain rule. We are interested in how that error is going to be affected by Wji, the impact on this on the final computed error. Okay, so we say we compute derivative of the error function with respect to Aj, this Aj here, and then the derivative of Aj with respect to W, we compute with respect to Wji. You can see here, that's the chain rule. Simplified single connection path, all right? Let's see, the term Aj, that function Aj is expanded as Wj1 plus Wj1z1, okay? In reality, that node, this single node here, is going to be receiving inputs from how many neurons? It's going to be receiving inputs from many neurons from the previous, because we are going back, right? So previously we were looking at the forward pass, how the functions are going down towards the output, and we looked at this as matrix vector products followed by nonlinear operation. But this node here, this Wji really is representing the various weights for connections to various. So there's another node there, another node there, another node there, another node. There are many. Okay. So that operation Aj is Wj1z1 plus Wj2z2 all the way to plus Bj, Wji Zi in general. All right. Multiple connections. That's what this is saying. Okay, so we take the derivative with respect to the specific weight, wji. All other terms drop out. Let's say, for example, we are taking a derivative with respect to wj1. If we are taking a derivative with respect to wj1, in this case, all these other values disappear to 0 because they do not depend on j1, do they? If you take the derivative of this function aj with respect to wj1, the final value is going to be z1 because all these others are zeros. They are not functions of wj1. If you take with respect to wj2, it's z2. wj3, it's z3, and so on and so forth. In general, if you differentiate with respect to wji, your value is zi in general. That's what this is saying. All other terms drop out. So the first part of our derivative is simply the incoming signal zi. I mean, just look at that. It's just one of those beautiful outcomes that you get. All right. This is saying that if we go all the way to the errors and we want to understand how that error is affected by a single weight, it's simply saying you really don't even have to compute that derivative because that derivative is always going to be the zi, the post-activated value. All right. The effect of this weight is the value zi, the incoming signal from the previous neuron. Okay, the local error signal. So the remaining part measures how a change in pre-activation AJ. So we remember here that we've just computed how AJ itself varies with respect to the AJ itself, the post-activation value varies with the weight. We got the value. But we haven't computed how the error itself varies with AJ, okay? Because that's what completes the computation in the chain rule. Okay, we define this as a local error signal. We just refer to it as delta J for now. We'll compute it later, all right? Okay, should be winding up. Substituting both components back into the chain rule, we see is going to be this value W, not sigma, this is delta J by Zi. All right. What is it saying? Let's just unpack this value and see what it's saying. That the derivative is the local error at receiving node multiplied by the input signal from the sending node. If we just focus on this connection alone, the derivative of E, which is the error with respect to the weight, all right, is the same as taking the local error at the receiving node here multiplied by this input signal coming from here. That is what it's saying. Just visualize that. I think it's a beautiful relation, but we need to move forward. For the bias Bj, we know that dAj, how Aj varies with respect to Bj is going to be 1. Why is it 1? Because if we look at that linear combination that we saw earlier, if we look at this function here, if you differentiate Aj with respect to Bj, there is only one element in this whole combination here that is a function of Bj, and it's this one. So if you differentiate with respect to Bj, it's what? It's just 1. That's what it's saying. All right. Okay. Its derivative simplifies directly to the local error signal. So dE, dBj, we call this another error signal. We'll compute its value. Now we need to go backwards in backpropagation. Fortunately, you are not going to be writing all these calculations when you train on your neural network. All the heavy lifting is done by your library. Scikit-learn, or it's PyTorch or TensorFlow. It's doing all these things for you, unknown, behind the scenes. Okay? So anyway, in the final layer, if we just look at the final layer itself, its pre-activation AK directly influences YK. YK is your output element, right? So the derivative with respect to AK is dE dyk, and then dyk dak. Now we see what these values actually represent. Look at E. E, we said, is the sum of square differences. isn't it? It's yk minus tk. Yk is the predicted value, tk is the correct target value. Okay? If you perform this derivation here, what do you get? Let's see. dE dyk is really yk minus tk. In fact, it's honestly one of the reasons why this 1/2 is here conveniently. If you perform this derivative, this 2 comes here and multiplies that. So you have 2 times 1/yk, and then yk minus tk, if you perform the derivative there, it's a chain rule operation I'm saying here. It becomes yk minus tk. And then dyk, dak, all right? dyk dak is 0, is 1. Why are we saying it's 1? Because yk is ak, or rather ak is yk. As in, we are saying if you go to the output layer of your neural network, the post-activated value there is the same as the the value that's been activated there after going through an activation function is the output itself. It's yk. All right? So yk is equals to ak, and so dyk dak is 1. It's like saying dyk dyk. It's the same thing. Okay? So we need to multiply those two. That so this in this case here, this value which is the local error at the output neuron is yk minus tk, is literally the error at the neuron. That's it. If we go to the hidden layers and we track again the sending node and the middle and the sending node and the receiving node. So here, let me just, I guess it's easier to visualize here. We're interested in what is happening here. So you have the sending node, you have this node here in the middle, and you have the receiving node. Sending node outputs the signal Zi across the weight Ji. Okay, so this is the sending node, this one here. The sending node I. This is the middle neuron that is under evaluation. We are actually interested in what is happening there. And then we're interested in what is happening here. And then these are further downstream. How node J impacts multiple receiving neurons K. Okay. At this point, I think my time is up. So what I'm just going to do is going to rush through some of these things. But essentially, what we end up, because we are interested in this error, this local error at the neuron of interest. You know, because we are going backwards in our computation, in backpropagation. We are interested in how the error is affected by the output, the pre-activated output of each neuron. All right. So, okay, I'm wondering how to summarize this. But essentially, if we look at because if you look at this chain rule multiplication here, we're saying the impact, I guess here, let me just add one more. There. Node I, node J, and node K. There. Okay? This is W, J, I, and this is W, K, K, J. All right? A, I, A, J, A, K. All right, if we just look at that drawing there, we're simply saying that the error function is going to be composed of is going to be composed of the impact on the error function itself by these outputs here, the output at AK and the output at AJ. All right, and you know when you look at that summation there, basically we're saying we can take the output at AK as the sum of the weight Kj multiplied by Zj. Zj is going to be the output of this neuron here, plus really, everything else all right? And essentially, but essentially, you know, if we just focus on this final relation that is at the bottom of the page here, what we are saying is that if we decompose this, what is happening here in the chain rule and focus on this value itself, the impact of AK, the impact of AJ on AK, it's such that it's really just going to be this weight here multiplied by the derivative of the activation function coming before it. That's all it's saying. Like, it looks complex, but that's all it's saying. The impact of AK, the impact of AJ, if you look at what is happening just down this stream here, the impact of, I guess it's the impact of AJ on AK here is going to be the product of that weight, WKJ, multiplied by the activation function here at the input, at the neuron of interest, which is the neuron J in this case. That's what it's saying. You know, okay, so and then we need to plug this back into the summation, yeah? And the intuition behind here is that to find the hidden local error, delta J, take all the errors from the next layer. That is what it's saying. You're interested in what is happening here, the impact of this, the impact of AJ here on the next layer. To find the hidden local error here on AJ, take all the errors from the next layer, okay? Multiply them by connecting weights, WKJ, sum them up, and scale the slope of the current activation function. Scale by the slope of the current activation function. This is all it's saying here. Multiply this WKJ multiplied by delta K of the next layer, because K is the next layer. We're interested in what is happening at J, and you scale it like that, all right? So step, the forward pass. This is the network training. Pass your input X downstream through the various layers of the neural network. Compute the activations layer by layer. We've already seen what the forward pass looks like. And then the output error evaluation, compute the initial signals. You know, we are these error signals that we are talking about here. We've said that at the output layer, the error is the same as your local error. Your local error is just going to be the final error, all right, at the final layer. And then propagate these errors using this thing here that we are referring to as, to get the delta for every neuron. This is known as a recurrence relation. You're basically saying to compute the error here, take the activation function here, compute its derivative, and then compute the error in the next value, the error in the next value multiplied by the connecting weights. These are the connecting weights. And this is not the only connecting weight, because we have said every neuron here is receiving inputs from various, every neuron is receiving errors from various neurons in the previous layer, and then compute compute the gradient like this, and update the weights via gradient descent. Okay. I guess really we are done with gradient descent. I guess try to wind up in 5 minutes. Forward pass operations are proportional to the number of weights. In terms of complexity, you know, it's an algorithm. So we need to look at how the algorithm scales with inputs. The complexity of the algorithm scales with inputs. It's O of W, all right? Back propagation is also O of W. Why are we saying it's O of W? It's O of W because we are calculating gradients with respect to the weights, with respect to each individual weight, rather. And then if it's O of W, you know, O of W is how can I put it? In the context of data structures and algorithms, O of W is a good complexity. Let's just put it like that. You're not dealing with O of W squared or O of W cubed or O of W factorial. That would be more complex. If it was something like O of W squared, we'd probably think twice about using this. Okay. But if it's O of W, it simply means it's almost like it's a linear relation. Complexity, the number of operations we need to do is scaling linearly with the number of the number of weights. Okay. Okay. So basically, this is basically a summation of how neural networks work. You make a forward pass. You compute the error between the predictions and the true values using the loss function. All right. And then using the loss function, you can also go backwards again with back propagation. You go backwards, you update the weights here. You go backwards, you update the weights there. You go backwards, you update the weights there until you arrive at the beginning. And you can see that issue that we were talking about earlier about vanishing gradients is if you compute your gradients here and they are 0, or they are a very small value, by the time you get here, because you're doing the chain rule, by the time you get here, your gradients will be 0. You know, so we need to. That's why we need to deal with that vanishing gradient problem. All right. Okay. In neural networks, our goal is not to minimize training error. When you're training a neural network, don't just be happy that your training error is low. That's not the goal of neural networks. Our goal is much bigger than that. It's generalization. How does your network perform on unseen data? All right. And if it does not generalize well, that means you're experiencing overfitting. It occurs when the network performs exceptionally well on the training data, but it makes wild predictions on your unseen test data. Okay, so we know that we already discussed this. Bias, variance, trade-off, these things you guys already know. MLPs have a very high expressive power, as you already saw from the universal approximation theorem. It's possible that if you have a very, by the way, if you have a very low, if you have a small data set, your neural network, because it's very expressive, it has many parameters, it can memorize your data set very easily because it can tweak itself nicely to model the data set that you have. But the question is it going to generalize to unseen data? So there are a couple of techniques that are used to prevent overfitting. They're often known as regularization. I'm sure you've heard regularization from the other instructors as well. It's a collection of techniques used to control model capacity and prevent complexity. There is something known as L2 regularization, penalizes the weights. Essentially makes sure that the weights of the network are small, not large. Yeah. L1 regularization. L1 regularization can literally switch off neurons in the network. It can make the weights of certain neurons very, in fact, 0. I don't need to go into the details of that. Okay. There's also another practice known as early stopping. It means as you're training your neural network and your errors are coming low, it might get to a point where your errors begin to go up because of overfitting. Early stopping says at the point where your training error is the lowest, the network training stops. That's all it's saying. Dropout means you're turning off certain neurons, basically. Randomly as you're training, as you make a forward pass, you turn off certain neurons. What does it do? It prevents codependence. It prevents neurons from depending on each other. It prevents certain connections within the neural network from becoming too strong and making the network rely on them too much. Yeah, that's what dropout does. Okay, data augmentation, let me show you an example. Okay, that has gone there. Data augmentation simply means transform the data set in certain interesting ways so that it looks new. If it's a picture of a cat, you can flip it, you can zoom, you can do some translation, you know. You can move, you can do some translation within the image, basically. It's like you're translating an object within the image. Okay? It's similar to cropping, if you like. You can rotate it, you can change the colors, you can add some noise, you can shift colors. All that, from a single image, you have like 8 new images. All right? That's what data augmentation looks like. Okay? I guess dropout I've already mentioned. The momentum is a concept in basically making the optimization much faster. It's simply saying that if you are if you know your low surface, for example, momentum is saying basically that if you're doing your optimization and your loss surface looks like that, your objective is to get here to minimize the error. Momentum says, when you're here, move very fast, because we know we are very far from, because we know this, the gradient here is very large. So move very fast, take big steps. But as you get there, take smaller steps. That's what momentum is, all right? Okay. Adaptive learning rates, I mean, all those things. You can read some of these things for yourself. There's a very common optimizer when you're dealing with deep learning libraries like TensorFlow and PyTorch. You'll find one called Adam. It's a very common one these days. Yeah, I've talked about vanishing gradients. How to initialize the weights of neural networks. You can use Glorot initialization or Xavier initialization. There's another one called He or K-Ming initialization. These are just nice, clever ways to initialize your networks so that it's much easier to begin the training and arrive at a good set of weights in your networks. Okay, batch normalization, all of this. Okay, so anyway, in general, this is what we've done today. We've looked at adaptive basis functions and how to avoid the curse of dimensionality, matrix formulation of forward and backward passes, loss surface geometry and calculus derivation of backpropagation, and then regularization and advanced optimization for successful training. That was a lot of words. Anyway, I am done. Any questions? You'll do a practical on neural networks in the afternoon. So I guess that will be more fun. Less intense. Yeah. Yes. So this class was about MLP. This class was neural networks. The nice place to begin with studying neural networks is multilayer perceptron. The next class, which is going to be taught by Emerson, is going to be on advanced neural networks. So you learn about other neural networks that are not MLPs. Yeah. But if you understand the working of MLPs, you're on a good path. You're in a good place to understand the working of any other neural network. It's like, I'm sure you've understood the connection between neural networks and linear regression. What I didn't mention is that if you just have a single layer of a multi-layer perceptron and remove the activation function so that you're just dealing with the pre-activation values, this is the same as linear regression, as you can see, because you're doing a linear combination of values. So these things are sort of related. Yeah. Any other question? Okay, so if you go to the workshop website, web page, the notes for this class are there. Everything, like so you can read that content for yourself. You can look at the books that I have given. And yeah, I guess, wow, I have taken too much time. Thank you so much. You guys have fun.